So yesterday we saw potential energy and kinetic energy. Now let's talk about the law of conservation of energy. What is this law of conservation of energy? So sum of potential plus kinetic energy is equal to constant. Okay, so this is the law of conservation of energy, right? So for a conservative force, this is of course applicable for conservative force because we can define potential energy only for a conservative force. Okay, so see how. So for a conservative force, we know by work energy theorem, work done is equal to final kinetic energy minus initial kinetic energy. So suppose for small displacement dx, okay, so work done by conservative force is given by what? Fc is the conservative force dot dx is equal to final kinetic energy k2 minus k1, okay, and work done against the conservative force is stored as the potential energy. So work done against the conservative force is external force dot dx is equal to what? Final potential energy minus initial potential energy. So this external force can be written as what? Minus Fc, minus of the conservative force, right? External force that you need to apply is equal to what? It's equal and opposite to the conservative force. Like if you want to do work against gravity, then external force needs to be applied is equal to what? Plus mg. Gravitational force is minus mg, right? So external force is minus of the conservative force, okay. So minus fc minus fc dot dx is equal to u2 minus u1. Move that negative sign on other side, so you will get fc dot dx is equal to what? U1 minus u2. So from this equation you get fc dot dx is equal to k2 minus k1, and from here you get fc dot dx is equal to u1 minus u2. You equate these two, then what do you get? K2 minus k1 is equal to u1 minus u2, and then you move this k1 on this side, so it becomes positive u1 plus k1, and this minus u2 on this side, so it also becomes positive k2 plus u2. So what do you get? You get u1 plus k1 is equal to u2 plus k2, right? The sum of potential and kinetic energy is equal to a constant. For a particle under the influence of a conservative force, sum of potential energy and the kinetic energy remains conserved. Okay, that means this is called as the total potential energy, total mechanical energy. Okay, so the total mechanical energy of a particle is its potential energy plus its kinetic energy. So total mechanical energy of a particle under the action of only conservative force remains conserved. So this is the law of conservation of energy. It's very simple, right? Okay, this is the law of conservation of energy. So if there is some non-conservative force acting on the particle, then what will happen? Some energy will be lost doing work against that non-conservative force. Okay, for an example, friction. So if there is friction involved, then some energy will be lost, right? Okay, so now let's apply this law of conservation of energy to the vertical circular motion. Okay, so suppose you have some object, it's moving in this circle, in this vertical circle. For an example, you take a stone, you tie a string to it, you whirl it in vertical circle. Okay, so now where will be the tension in the stone maximum? What do you think? So if you just see its free body diagram, just think about this thing. Okay, when it is at bottom, then tension is acting upwards. Okay, it is maximum at bottom, so tension is acting upwards and its weight is acting downwards. Tension acts upwards, its weight acts downwards, right? So now this tension is directed towards center, mg is directed away from center, and therefore the net force towards the center, that is the centripetal force, is equal to T minus mg at the bottom, right? Okay, so at the bottom you have centripetal force FCP is equal to T minus mg, and therefore what is T? T is equal to FCP plus mg. Okay, so that's the tension. But at the top, at this point you have tension directed towards the center, okay, that is downwards, and gravitational force is also acting downwards. So at this point, at the topmost point, both the forces, tension and mg, they are providing, combined, they are providing the centripetal force. So therefore you have centripetal force FCP at the top is equal to what? Tension at the top plus mg, right? So what is tension? So tension at the top is equal to FCP minus mg, right? This thing is clear. Okay, tension will be lesser at the top, right? So now see, now we are interested in finding out two things. One is the minimum speed of this particle in the vertical circular motion, and second thing is the difference between tensions at topmost point or the highest point, lowest point, right? So let's see. So now we have just seen that at the topmost point, at the highest point, the tension and gravitational force both are directed towards center, right? So we can say FCP means the centripetal force at this point A is equal to tension at A plus mg, right? Centripetal force is equal to tension at A plus mg, okay? And then for the minimum speed, tension must be equal to 0, okay? For the minimum speed at the top, the tension must be equal to 0, right? Yes, no? Because speed is minimum means now in these two things you cannot change mg. Mg is a constant. What can you change? You can just change tension in the string. Okay, so when you are moving it, tension depends on how fast you are moving it, okay, or how fast you are pulling it towards the center, you can say, right? So this thing is clear. What can you change in these two? Mg cannot be changed, you can only change the tension, okay? Now suppose tension is minimum. What can be the minimum tension? Tension is suppose 0, okay? So you are moving in that particle, not particle, stone which is tied to a string, and other end of the string is in your hand. So you are moving that string such a way that stone just passes over the topmost point, okay, just passes and it doesn't fall down, okay? So for that the tension that you are applying is equal to 0. So then what provides the centripetal force? Only what provides for the centripetal force? Only the gravitational force, okay? So therefore centripetal force, which is mv square by r, is equal to just mg. You are moving it in such a way that it just passes over that topmost point. So you are not exerting any extra force, you are not pulling it, or you are not exerting any extra tension, right? So tension is 0, okay? So then what do you get? You get mv square by r is equal to mg, and therefore now gets cancelled. Take r on other side, so you get v square, that is va square. Va square means a is the position at the top, so va square is equal to rg, and therefore va is equal to square root of rg, okay? So minimum speed at the top is square root of rg, right? This is clear. Okay, good. Then now I have to find out minimum speed at point C, suppose. So what I will do, I will just apply the law of conservation of mechanical energy. So what is the law of conservation of mechanical energy? The sum of potential and kinetic energy remains conserved. So I can say the potential energy at C plus kinetic energy at C is equal to potential energy at A plus kinetic energy at A. So what is kinetic energy at C? Kinetic energy at C is potential energy at A. Then I will move this UC on the other side. UC means potential energy at C. That will become negative. So what do I get? UA minus UC. Okay, so kinetic energy at C is equal to UA minus UC plus Ka, right? UA minus UC plus Ka. And then I put the values. What is kinetic energy? So it is half of mv square. I want kinetic energy at C, so it is half of m into Vc square, and that's equal to potential energy at A. Okay, so that is mgh at A, and potential energy at C is mgh at C. I take mg common. Okay, I move mg outside, so you have Ha minus Hc, right? And then you have plus kinetic energy at A, that is half of m into Va square, right? So m and m can be cancelled throughout. Okay, after that you multiply this whole equation by 2. So what do you get? You get Vc square is equal to 2 times, I have multiplied by 2, whole equation I am multiplying by 2. So Vc square, because the 2 and this divided by 2 gets cancelled. Okay, so Vc square is equal to 2 times of this thing, g into Ha minus Hc. Okay, height at A minus height at C, plus we just found what is Va. So Va is equal to square root of Rg, or Va square is equal to Rg. So put that. Okay, Va square is Rg or Gr, right? Then what is Ha minus Hc? So height at A minus height at C is this much. Okay, this much is the difference between heights. How much is this? It's equal to R, right? Height at A minus height at C. So this much difference is equal to R. Okay, radius of the circle. So Ha minus Hc is equal to R. Just put that. So you have 2gr plus gr, 3gr, that is Vc square. So Vc therefore is equal to root 3 gr. Okay, this thing is correct. Is this thing clear? This is correct, of course, right? So this is minimum speed at the midway position. Okay, the point C is root 3 gr. And then similarly, what will be the minimum speed at the bottom point or the lowest point of vertical circular motion? It's equal to root 5 gr. Okay, minimum speed at the bottom is root 5 gr. We can calculate it in the similar way. Okay, just taking kinetic energy plus potential energy at B and equate it to sum of kinetic and potential energy either at C or at point A. We can find out the minimum speed at the bottom, minimum speed at the lowest point is root 5 gr. Okay, this thing is clear, everyone? All right, good. So we need to remember minimum speed at the top is root gr, minimum speed at the midway position is root 3 gr, and minimum speed at the lowest point is root 5 gr. Okay, then now let's talk about the tension in the vertical circle. Okay, so we just saw that here at the topmost point, that is at point A, FCP, the centripetal force, is equal to what? Sum of tension at A plus mg, right? Then you can put the value of centripetal force. So mv square by r, m into Va square by r will be the centripetal force at A, right? So therefore what is tension? So tension is T at A. Then you move that mg on other side, so you get tension at A is equal to mva square by r, okay, minus mg, right? mva square by r minus mg is the tension. Okay, then if you talk about point B, then at point B tension is directed towards center, okay, and mg is directed away from center. So you have centripetal force is equal to difference of these two. So tension at B minus mg, right? So centripetal force mvb square by r is tension at B minus mg, okay? And therefore if you want tension at B, so tension at B is equal to mvb square by r plus mg, okay? mvb square by r plus mg, right? Then I want difference in tension at A and B. So what I will do is, this is my equation 1, this is equation 2. I will subtract equation 1 from equation 2, okay? So TB minus TA, tension at B minus tension at A, is equal to, here on right hand side I have mv square by r, mvb square by r minus mva square by r, and then I have mg minus mg, so that will become plus mg, right? So mg minus mg, so that is 2 mg, and then I have m into vb square by r minus m into va square by r. Out of that I can take m by r common. Then you have vb square minus va square, okay? vb square minus va square, right? So what is this thing? Okay, what is this thing? vb square minus va square. So that is equal to square root of 2 times g into difference in heights, right? This is equal to square root of 2 times g into difference in height, okay? Sorry, root of 2 times g into difference in height. And what is difference in height? It's equal to 2r, okay? This thing is clear. Is this point clear? vb square minus va square would be equal to, not square root of, I am taking square, no? So that square root will vanish. vb square minus va square is equal to 2g into 2r. Okay, so let me explain this. Okay, so what do I want to find? I want to find out vb square minus va square, or I will take that m also inside, right? I will take that m also inside. So I have half of m into vb square minus half m va square. So you can say difference in kinetic energies at final minus initial position. So this you can say it's equal to k2 minus k1. It is equal to u1 minus u2, right? Yes, no? Because you have law of conservation of energy, k2 plus u2 is equal to k1 plus u1, and from this one you can say k2 minus k1, move this k1 on this side, it is equal to u1 minus u2, okay? So this is equal to, this is kinetic energy at B minus kinetic energy at A, so it's equal to potential energy at A minus potential energy at B, right? So then now this is my circle, this is the point A and this is point B. How much is the difference in heights of these points? It's equal to 2r, right? How much is the difference in heights? It's equal to 2r. Therefore it is mg multiplied by 2h, sorry, mg multiplied by h at A minus h at B. So what's the difference? Tell me. So it's equal to 2r, okay? It's equal to 2r. So you have mg multiplied by 2r, right? Difference in heights of A and B, okay? So then if I would just want vb square minus va square, I can take that half m common, I can cancel out m everywhere, then I can move that 2 on that side, so I get 2g times 2r, right? Is this thing clear? vb square minus va square would be equal to, I can just cancel out m on both sides, move that 2 on that side, so vb square minus va square is equal to 2 times g times 2r, because I have moved that 2 in the denominator on the other side. Okay, is this thing clear? Yes, no? Right. And therefore, what is Vb square minus Va square? 2g times 2r. Okay. Then what you can do is, okay, so see, half of m into Vb square minus half of m into Va square is equal to potential energy at A minus potential energy at B, right? And what is potential energy? It is mg h at A minus mg h at B. So I have taken mg common, right? So then what you can do is you can cancel out m on left hand side and right hand side. Okay, so m you have cancelled out. Then you can move this 2 in the denominator on right hand side, so it goes to the numerator, right? So therefore now okay, so then if I want Vb square minus Va square, I will move this 2 in the denominator on other side, and m I have already cancelled out, so that's equal to 2g times 2r, right? Okay, good. So that's equal to 2g times 2r, and then if you simplify this r and r gets cancelled. So this is 4 times g into m, that is 4 mg. So 4 mg plus 2 mg means 6 mg. Okay, so what is difference in tension? Difference in tension at this point and this point is equal to 6 mg. Okay, difference in tension at B and at A is equal to 6 times the gravitational force, or 6 times the weight of this object or the stone. Okay, this is clear, right? So you just need to remember that number. Okay, and we need to be able to write down the equation, okay, for the centripetal force at this point, at this point, and at this point. Okay, tell me what will be the centripetal force at this point, at point C. At this point, what will be the centripetal force? Here it is tension plus mg, here it is tension minus mg. Okay, good. So at point C it is just equal to tension. Very good, right? At point C it is just equal to what? It's just equal to tension in the string, because mg acts in perpendicular direction, right? Okay, so then we found the tension at B minus tension at A is equal to 6 mg, right? It is equal to 6 mg. And if you take point D or point C, then difference in tension between this and this one would be 3 mg. Difference in tension between this and this one would be equal to 3 mg. Okay, and we can just find it out, right? So using the similar method we can find it out. Difference in tension at this and this point is 3 mg. Difference in tension between this and this point is 3 mg. Now notice that we haven't taken the minimum speed here. Okay, so we didn't consider the minimum speed at A, minimum speed at point B, etc. Okay, for any speed, because we just took the general formula mv square by r, right? So this is applicable for any speed. Right? So you move the object with whatever speed in vertical circular motion. That means if you take a stone, tie it to a string, move it with any velocity in vertical circular motion, so this formula is applicable. Okay. Okay, good. After that, let's talk about the spring mass system. Okay, so this is the spring connected to a mass, and what you do is you move this mass towards right. Okay, you just stretch the spring, right? When you move the mass, the spring will be stretched, because the other end of the spring is connected to a rigid support, so other end will not move. When you move the mass, what will happen? Spring will be stretched. So now, in last lecture we learnt that there is some force, the restoring force generated in spring, right? And that restoring force will oppose, it will oppose this stretching of the spring. Okay, so by Hooke's law, the spring force is equal to what? It's directly proportional to minus of the displacement. Okay, why minus? Because if displacement is towards right, the spring force tries to restore it back, so it will act towards left. Okay, so therefore the spring force is equal to minus of kx, right? When you remove the proportionality sign, put an equality sign, a constant will enter. Constant is known as spring constant. Okay, now when you displace it, some work is done. Okay, some work has to be done against the spring force, and for small displacement dx, work done against the spring force is equal to minus of spring force dot dx. Okay, so spring force is minus kx, so external force that you need to apply is equal to what? Plus kx. So work done is equal to what? External force multiplied by dx, so that is kx dx, right? This thing is clear. External force is equal to plus kx, so work done is equal to what? Work done in stretching the spring by small displacement dx is equal to kx dx. Kx is the force that you need to apply. Okay, everyone? This is clear. There is a problem. Is there a problem? No problem, right? Okay, then work done in displacement from 0 to x, so that was for a small displacement dx. Now if you move it from the 0 to x, how much would be the work done? So work done is just integral of this kx dx from 0 to x, 0 to capital X you can say. So when you integrate this, you can move k outside, so integral of x dx is just x square by 2, and then you can put the capital X in place of x, that is you can put the upper limit and lower limit, but lower limit is just 0, that means you need to put only the upper limit. So that's why work done is equal to half of kx square. And we learned that this work done is stored as the potential energy. Okay, work done against a conservative force gets stored as the potential energy, or it increases the potential energy. So we can write this work done as final potential energy when displacement is x minus initial potential energy when displacement is 0. Okay, work done is equal to what? Final potential energy when displacement is x minus initial potential energy when displacement is 0. So this difference in potential energy is equal to the work done means half of kx square. Okay, and now comes the crucial point, that for convenience, for our convenience, we choose that potential energy at x equal to 0 is 0. Okay, so this is simply for our convenience, that potential energy at x equal to 0 is equal to 0, right? When we choose that, we get this simple formula for potential energy of spring, that u of x is equal to half of k into x square. Okay, potential energy at displacement x is equal to half of k into x square. So we need to remember this formula, but we need to also remember that we cannot explicitly find out the formula for potential energy. What we can find out is difference in potential energy only. Okay, and this potential energy at x equal to 0 means unstretched spring, that we need to define. So that will be some constant, some value. So when we take that value, in respect to that value, we can find out the potential energy at displacement x. Is this thing clear? Yes, no? Okay, everyone? Right, good. Okay, so see, again, in case of gravitational potential energy also, suppose you move the object from here to here. Okay, so it was at height h1, then you move it to height h2. So how much is change in potential energy? Change in potential energy is equal to mg h2 minus h1. Then you can choose that potential energy at height h1 is equal to 0, right? And in reference to that, I can just say that h1 is equal to 0. So potential energy at height h1 is equal to 0, or I can just say that potential energy at h1 is 0. So what matters is the difference in potential energy, not the particular value of potential energy. Okay, because what you can find out is u1 minus u2, difference in potential energy, is equal to k2 minus k1, right? You can only relate the change in kinetic energy with change in potential energy, or work done with change in potential energy. You cannot relate work done with explicit value of potential energy at one point. Work done is always the difference in potential energy, right? Work done is never equal to potential energy. Okay, so this thing is clear. What matters is difference in potential energy only. Okay, so this is for our convenience that we choose that potential energy at x equal to 0 for a spring is equal to 0. Okay. Is there any confusion in that? Anyone? All right, good. So then, so for a force acting on two springs is equal, if the force is equal, then we can use this formula for potential energy. So we know that force is equal to k into x in magnitude. Okay, so you can multiply by k and divide by k. What do you get then? So in numerator it is k square x square, or it is kx square, means 4 square, and then you get u is equal to 4 square divided by 2k. U is just equal to 4 square divided by 2k, right? Which thing? This one. So what I am saying is, if force acting on two springs is equal, how to compare their potential energies? So then, you know, force is equal to k times x, right? Force is equal to k times x. So you can just multiply with k, the numerator and denominator. So multiply by k and divide by k. So this thing will become k square x square. Okay, k square x square divided by k, right? And what is k square x square? It is 4 square. Okay, and therefore you can use this formula, u is equal to f square divided by 2k, right? So that's simple. Welcome. Okay, so now let's solve some problems based upon these things. Okay, so what is the minimum velocity with which a body of mass m must enter a vertical loop of radius r so that it can complete the loop? Tell me. Anyone? Option B, right? Option B. Okay, because we have seen that if you take a vertical circular motion, then the speed, minimum speed at this point is square root of gr. Minimum speed at this point is root of 5 gr, and the body must enter minimum with this speed, right? So we need to be sure that it completes the circle. We don't know where does it enter from, right? Whether it enters at this point, whether it enters at this point, and whether it enters at this point. So if it enters at this point, the minimum speed should be equal to what? Root 5 gr. Okay, so if you want to be sure that it completes the circle, then minimum speed is root 5 gr. So that is very simple, right? So this is from NEET 2016. Let's see next one. A mass m is attached to a thin wire and whirled in a vertical circle. The wire is most likely to break when inclined at an angle of 60 degrees from the vertical, mass is at the highest point, the wire is horizontal, mass is at the lowest point. Yeah, the mass is at lowest point. Very good, right? Because tension is maximum. Yes, very good. So tension is maximum at the lowest point. So string is most likely to break when the mass is at the lowest point. So option D is the answer. That's very simple. Let's see next one. A body initially at rest and sliding along a frictionless track from a height h. So it is sliding along this track from height h. Okay, sliding like this. Just completes a vertical circle. Of diameter AB equals to D. The height h is equal to. Tell me. So that's very simple. So here what you can say is the object only has potential energy at this point, and you can choose this height to be equal to 0. So object only has kinetic energy at this point, right? So its energy gets converted from potential at top to kinetic at bottom. Okay, so you can say that potential energy at top or at height h is equal to kinetic energy at point A. How much of kinetic energy do you need? So half of m into VA square. What speed do you need at this point to complete the circle? It's equal to root 5 Rg, right? Just put that. Potential energy is mgh at A, right? So mm gets cancelled. Then put the value of the speed that you need. So that's equal to root 5 Rg at the bottom. So square of that is 5 Rg. So that is gh at A. So gg gets cancelled, right? So height at A is just equal to, okay, 5r by 2. And is there that option? No, it is in terms of diameter, no? So it's 5r divided by 2 means radius is half of the diameter. So it's 5 times d by 4. That would be the option answer, right? Yes, no? Okay, so that is simple, right? So same concept is repeated again and again. Okay, what's the minimum speed in the vertical circular motion? All right, let's see next one. As shown in the figure, the mass is performing vertical circular motion. This mass is moving in a vertical circle. The average velocity of particle is increased. Then at which point will the string break? So again this is repeated. We know that it is point B. Okay, because tension would be maximum at point B. B means the bottom, right? Okay, let's see next one. A child is sitting on a swing. Its minimum and maximum heights from the ground are 0.75 meter and 2 meter respectively. Its maximum speed will be, tell me. Child is swinging on a swing. Tell me. Child is swinging on a swing like this. Yes, I'm just drawing the diagram so that I allow you to think for some time, right? So this is the child. Option B. Okay, let's see. So the minimum and maximum heights. So this swings like this. Okay, so suppose it swings like this, something like this. So this is the minimum height from the ground. Okay, so let's suppose this is the ground, this is minimum height, this is maximum height. And how much is difference between heights? So difference between heights is, let's say h at this point is a. Okay, so this point is a, this point is b. So height difference is ha minus hb, right? Height difference is ha minus hb, and therefore its maximum speed will be, where will be the speed maximum? At this point. Okay, so when it goes here, you can say it stops for a while. For a while means momentarily it will stop and it will come back, right? So the energy is purely potential at point A, and when it comes to the point B, we can say that height of B is 0. Okay, so energy becomes purely what? Kinetic. Okay, so I can say potential energy at A is equal to kinetic energy at B, or what we can say is potential energy. Okay, let's take potential energy at A is equal to potential energy at B, because height is given, no? So potential energy at B plus kinetic energy at B plus half of m into Vb square, right? So then mgh at A is equal to mgh at B plus half m Vb square. Gets cancelled out, right? Then you move the GHB on other side, so you get half Vb square is GH at A minus H at B. That means Vb square is equal to 2 times GH at A minus H at B. Okay, and then if you want square root, the square root is just this thing. I mean, if you want Vb just square root of the other side, and that's equal to square root of 2 times G is 10, Ha minus Hb is 2 minus 0.75. So how much is that? 1.25. 1.25 times 2 is 2.5. 2.5 times 10 is 25. Square root of 25 is 5 meters per second, right? So correct. So I guess 2-3 students found the answer, right? Correct answer. So it is equal to 5 meters per second. That's the answer, option B. Okay, so this is simple, right? Yes, no? Okay, good. Alright, let's see next one. A stone is tied to a string of length L and is whirled in a vertical circle with other end of the string at the center. Okay, other end of the string at the center. So it is just stone tied to a string whirled in vertical circle. At a certain instant of time, the stone is at lowest position and has speed u. Okay, stone is at the lowest position and it has speed u. The magnitude of change in velocity as it reaches a position where the string is horizontal. Okay, so what would be the change in velocity, magnitude of change in velocity when the string becomes horizontal? So this is the question. All right, we have a stone tied to a string whirled in vertical circle. At a certain time, the stone is at the lowest position and has speed equal to u. The magnitude of change in velocity as it reaches the position where the string is horizontal. This is the question. All right, so when stone is at this point, it will have some velocity, and they are saying that the speed is u. Okay, so suppose it is moving in anti-clockwise sense like this. So at this position the velocity will be directed like this, and this is u. Okay, this is u. Let's call it u bar. At this point, when it goes at this point, the velocity will be directed upwards. Okay, it is always tangential, right? The velocity is directed like this. So suppose this is v bar. Suppose this is v bar, and what we want is magnitude of change in velocity. We want magnitude of change in velocity. This is the question. So what is change in velocity? V bar minus u bar. Okay, so if v bar is directed like this, v bar is directed like this, and this would be the minus u bar. Okay, this is minus u bar. Then what is v bar minus u bar? It's this one. Okay, right? Yes, no, by parallelogram law of vectors addition, this much, right? How much is that in magnitude? It's just equal to v square plus u square. Okay, so in magnitude I can say delta v is equal to square root of v square plus u square, right? It is square root of first vector square plus second vector square plus 2 times magnitude of first vector into magnitude of second vector multiplied by cos of the angle between two. Angle is 90 degrees, right? Therefore it is just magnitude of first vector square plus magnitude of second vector square. Okay, and then you need to find out what is that v in terms of u, because what you are given is just u, right? So speed at the bottom. So then you can say that when an object moves from here to here, there will be increment in speed. How much? So you can say u square is equal to v square plus 2gh. And how much is height difference between these two? So height difference is r. Okay, that r is equal to length of this string, you can say. So therefore v square is equal to u square minus 2gh, and h is equal to L. Just put that over there. What do you get? Therefore delta v is equal to square root of v square is u square minus 2gl, and plus you have another u square. Okay, so delta v is equal to square root of u square plus u square is 2u square. Okay, 2u square minus 2gl, or 2 you can take common, right, from the options. Yes, 2 you can take common, so it is u square minus gl. So this is the answer. Okay, so is this question clear? Yes, no? Everyone? Right? Okay, good. So this was a little bit good question, you can say, till now, right? Okay, let's see next one. Two springs A and B have spring constants K and KB respectively, and K is equal to 2 kb. This is given. They are stretched by applying a force of equal magnitude. Okay, so they are stretched by applying a force of equal magnitude. If energy stored in spring A is EA and energy stored in spring B, then energy stored in spring B will be. This is the question. So we just saw, right, that if forces are equal, then which formula should we use for the potential energy? E is equal to half of F square by K. Okay, we must use this formula. So if force is equal, then energy is inversely proportional to K, right? And you want EB, so EB divided by EA is equal to what? It's inversely proportional, so it is Ka by Kb. So very simple question, and K is equal to 2 Kb, right? So Ka by Kb is 2, or put K is equal to 2 times Kb, so that Kb gets cancelled, and therefore from that you get Eb is equal to 2 times Ea. Okay, very simple. Eb is equal to 2 times Ea. Is this thing clear? Everyone? All right, good. So this is very simple if we know this formula, right? Okay, let's see next one. Then now, based upon spring, the questions would be simple. When a long spring is stretched by 2 centimeters, its potential energy is U. If the spring is stretched by 10 centimeters, the potential energy stored in it will be. Tell me. So U is equal to half of K into X square, right? So it is directly proportional to X square. If it is stretched by 2 centimeters, potential energy is U. So what will be U dash? U dash is equal to half of K into X dash square, you can say. And X is 2, X dash is 10, means you can say it is 5 times of X square. Okay, X dash is 5 times of X, right? Because it is 10 centimeter, no. So it is 5 times of X square, and therefore you can put you can just take square of that, so you will get 25 times half of K into X square, and that is equal to 25 times of U, right? So answer is 25U, option D, right? So that is very simple, and we shouldn't even take this much time. So we can just say that, oh, it is directly proportional to X square. So earlier it was 2, now it is 10. It's directly proportional to X square, no? So X increases 5 times. Okay, X becomes 5 times, so energy must become what? 25 times. That's it, right? Okay, very simple. Let's see next one. A mass of 0.5 kg moving with a speed of 1.5 meter per second on a horizontal smooth surface collides with a nearly weightless spring of force constant 50 Newton per meter. The maximum compression of the spring would be. So this mass, it's moving with some speed, okay, and horizontal smooth surface, on the horizontal smooth surface, so there is no loss of energy on this horizontal smooth surface. Then it collides with the spring. So what will happen? The spring will be compressed, right? So till what time the spring gets compressed? Till the time this mass has some energy left, right? Because it will have to spend its energy in order to do some work against the spring. Okay, so ultimately you can say, when its energy becomes 0, the compression in the spring would be maximum, right? Compression in the spring would be maximum when energy of this ball becomes 0. So its total energy gets converted to energy of the spring, right? Okay, this thing is clear, everyone, right? So I can say that potential energy of spring when it gets compressed completely, okay, completely means by maximum amount, it should be equal to the initial kinetic energy of that mass. Okay, so that mass will lose its kinetic energy and do some work against the spring. So it is equal to half of k times x square, and that's equal to half of mv square. Okay, m is given, v is given, and k is given. So x we need to find out. Half of gets cancelled, and x square is equal to mv square by k, means x is equal to the square root of that. So therefore x is equal to square root of mv square divided by k. Then just put the values and we'll get the answer. So mass is 0.5, v square means 1.5 square divided by k, or we could just take v outside, right? Square root of v square, 0.5, and divided by, in denominator you have 50. Okay, so this thing gets cancelled and 10 will be left. Then 0.1, 10 divided by 0.1 means 100 in the denominator. Take square root of that. So it is square root of 1.5 square is 1.5 divided by square root of 10 is square root of 100 is 10. So it is 0.15. 0.15 meters would be the answer. Right, this is the answer. So it's option A. Okay, so it's very simple. Right. Okay, good. Let's see next one. So this question is kind of repeated. The potential energy of a long spring when stretched by 2 cm is U. If spring is stretched by 8 cm, that means displacement is 4 times. The potential energy stored in it is how much? Option D, right, 16U. Okay, let's see next one. A vertical spring with a force constant K is fixed on a table. Okay, so a spring is fixed on a table. A ball of mass m at height h above the free upper end of the spring falls vertically on the spring. So you have vertical spring. This is the vertical spring fixed on a table, and a ball of mass m is at height h above the fixed end. So suppose it is here, right? So this much height difference, this height difference is h. Okay, then what you do, then so that the spring is okay, h above the free upper end, at the free upper end of the spring falls vertically on the spring. So this ball falls on the spring, so that the spring is compressed by distance d. So the ball falls and the spring gets compressed. Okay, so this was first case, and then what we can do is we can draw the second case when it gets compressed, spring gets compressed, right? So suppose spring becomes this much, it gets compressed. Okay, so right, so compressed by distance d, it gets compressed by distance d, this much. Okay, so the question is the net work done, in the process is, tell me how much is the net work done in this process. Okay, tell me what are the forces there. One is the gravitational force, right? It's doing work. So work done by gravitational force is what? It is mgh when the ball comes till here. Then again mg d. D is the difference in height between this and this point, right? When the spring was not compressed and when the spring gets compressed, the difference in height is d, right? So how much is work done by gravitational force? It is mgh plus d. And how much would be the work done by the spring? It's option A. Okay, let's check. So work done is work done by gravitational force plus by spring force. Okay, so work done by gravitational force is mg h plus d, mgh plus mgd, right? Then plus work done by the spring force. So now is the spring force doing work? No. Okay, so spring force will be always directed opposite to that of the external force. Okay, if external force is pulling it down, spring force will be directed upwards. Okay, so work is being done against of spring force. How much is that work done? Or you can say work done by external force in compressing the spring would be what? It is half of kd square. Okay, because d is the displacement. What will be work done by the spring force? It will be negative, right? So it will be negative of half of k into d square. Okay, this thing is clear? Yes, no? Okay, everyone? Right, so that's why it is option A. Option A is the answer. Okay, is there any confusion? Anyone? All right. Okay, good. So let's see next one. A body of mass 1 kg is thrown upwards with velocity of 20 meters per second. It momentarily comes to rest. It momentarily comes to rest after attaining a height of 18 meters. So you throw an object and it goes to height 18 meters. It comes to rest. How much energy is lost due to friction? This is the question. How much energy is lost due to friction? Okay, so initially you throw it with speed v, so whatever it is, 20 meters per second. It momentarily comes to rest after attaining some height. So what can you say? That total energy is constant, right? So okay, but there is some energy lost in doing work against friction. So what we can say is initial kinetic energy, initially it had some energy, initial kinetic energy is equal to final potential energy because it's going to some height plus work done against the friction. Okay, so total energy that it had was the kinetic energy, initial kinetic energy. It is being utilized in two ways. One is attaining some potential energy and one is doing some work against the friction, right? So that's why we can say initial potential energy is equal to initial kinetic energy because it is thrown with some velocity initially from the ground, so no potential energy. Okay, or we can say potential energy at the ground is 0. So initial Ke is equal to final potential energy plus some work is done against the friction. So then what is kinetic energy? It's half mv square. it's equal to final potential energy is mgh plus work done against the friction is W. Then W is equal to half mv square minus mgh, right? We just want to find out how much energy is lost due to friction. Okay, so this much energy is lost, right? Work done against the friction in doing some work against the friction. Half of m is 1, v is 20, 20 square minus 1 times g is 10 times h is 18, right? And this is equal to 400 divided by 2 means 200, 200 minus that is 180, right? 10 times 18, so this is 20, 200 minus 180 is 20 joules. Okay, is this one clear? Okay, good. So this is also simple. Let's see next one. 300 joule of work is done in sliding a 2 kg block up the inclined plane of height 10 meters. Work done against the friction is. Okay, so you have a block and you slide it on this inclined plane and you slide it to the height of 10 meters. So from here, suppose you slide it till here. Okay, so difference in height is 10 meters, right? And there is some friction also. Okay, so there is some friction. So work done against the friction is, this is the question. So now total work done, work is equal to, you can say mgh, because you have gained some potential energy, that block has gained some potential energy, plus work done against the friction, work against friction. Okay, so let's say fs, right? Okay, actually when you are moving it will be kinetic friction, but let's say it is friction. Okay, so small f. So work done against friction, suppose it is wf. Okay, that is work done against the friction. What will be wf? It is total work done minus mgh. Just put the values. Total work done is 300 minus, it is 2 kg block, g is 10 and h is 10 meters, so that is 200, right? 300 minus 200 means 100 joules. The answer is option C. So after that, let's talk about the power. Okay, so name of the chapter is work, energy and power. So let's talk about power. So power, we know it is the rate of doing work. Okay, so just to give you an example, suppose this is student A, this is student B, and they want to move. So there is suppose some temple at the top over here, and there is the staircase. Okay, so suppose student A goes there in 1 hour, right? And student B goes there in 2 hours. So who is more powerful? The one who goes in lesser time, right? Because see here they are doing some work against the gravitational force. How much is the work done? Work done is equal to their mass. Okay, their mass multiplied by g into h, right? Now it depends on their masses. So if mass is equal, then you can say that student A is more powerful. Okay, and suppose mass of A is 80 kg, mass of B is just 50 kg, and they walk together. Okay, they walk together, suppose, then who has done more work? the one whose mass is greater, right? Okay, now see, this one has done more work, so this one has spent more power too, right? Okay, so what is the average power? Average power in time t can be written as, average power is just work done per unit time. Okay, so W divided by T, that's average power. And if you want instantaneous power is rate of doing work with respect to time. Okay, so dW by dt, and work done can be written as F dot x. Okay, so force times displacement. Then if you take derivative of that, then you get what? dF by dt times x plus F times dx by dt. Okay, and when the force is constant, you can write power is equal to just force times velocity. Okay, this thing is clear? Yes, no? So instantaneous power can be written as what? Force times velocity. Okay, this is clear, everyone? All right, we need to just remember this formula for power, that it's equal to work done divided by time, it's equal to dW by dt, and it's equal to force times velocity. Then we know that work done is equal to change in potential energy. Okay, and work done is also equal to change in kinetic energy, right? So in place of dW, sometimes we'll need to take du by dt. Okay, sometimes dk by dt. That means it is equal to power is rate of doing work, means it is rate of change of energy also. Okay, it might be potential energy, it might be kinetic energy. That's very simple, right? Okay, so using work energy theorem, we can say that average power is what? It is the final kinetic energy minus initial kinetic energy divided by time, because work done is equal to what? It is just equal to final kinetic energy minus the initial kinetic energy. Okay, this is work energy theorem. Work done is just equal to final kinetic energy minus the initial kinetic energy, and therefore power, we know average power is just work done divided by time, so it is change in kinetic energy divided by time. Okay, final kinetic energy minus initial kinetic energy divided by time. And if you want instantaneous power, so again what you can do is you can take rate of change of kinetic energy. Okay, so that is d by dt of half mv square. M you can move outside, m is a constant. Okay, if body doesn't break etc., m remains constant, so half m times d by dt of v square. Then what is d by dt of v square? So directly you cannot take derivative of v square with respect to t. Why? Because v and t are different variables. So what you do, you make use of chain rule. Okay, you take derivative with respect to v, that means you divide by dv, you multiply by dv. So when you take derivative with respect to v of v square, that is 2v. Okay, and what is dv by dt? dv by dt is acceleration. Okay, dv by dt is just acceleration a. So then you can write that this is mass times acceleration, this 2 gets cancelled, and therefore power is equal to force times velocity. Okay, so in two ways you can find out that power is equal to what? It's just force times velocity. Okay, but now you need to remember this formula too, because sometimes the kinetic energy can be given in terms of time and they will ask you to find out the power. So what do you need to do there? Just take the derivative of kinetic energy and that's it. Okay, is there any confusion in this? Any question? Okay, very good. Then there is one definition which we'll use in this chapter. Okay, and sometimes, so that is efficiency. What is efficiency? Efficiency of any process is just output divided by input. Okay, so there is another definition. Efficiency means what you get, okay, the result divided by what you are paying for. Okay, that is outcome, you can say, divided by efforts or whatever you are paying for. Okay, what's your expenditure? Physical expenditure, okay, or economical expenditure? That is just output power divided by input power, we can say. Efficiency in terms of the work done, it is output power divided by input power. So we can write output power as P out, input power as P in. So efficiency is denoted by eta. Eta is just equal to output power divided by input power. Percentage efficiency just eta multiplied by 100. Okay, so percentage efficiency, it is just output power upon input power multiplied by 100. So this is one definition that we need to remember, right? Okay, so then now let's solve some problems based upon this thing. So let's see this one. A body of mass 1 kg begins to move under the action of a time dependent force. So force is time dependent, where I cap and j cap are unit vectors along x and y axis. What power will be developed by the force at time t? Tell me. Basically you want to find f bar dot v bar. Okay, so how can we find it? Only force is given. What's given is a body of mass 1 kg begins to move. Okay, if it begins to move means it starts from rest, you can say, under the action of this force. Okay, so this is the force. So I can say what is the acceleration? It is just force by mass, right? How much is the mass? Mass is 1 kg only. So acceleration is also the same thing, 2t into I cap plus 3t square times j cap, right? Because mass is just 1. Okay, so acceleration has same magnitude as that of force. Okay, then now how can you find out velocity from here? So this is dv by dt. dv bar, I can say, by dt is 2t times I cap plus 3t square times j cap. Then move that dt on other side and integrate it. So integration of dv bar, okay, from u bar to v bar, or let's say from 0 to v bar, because a body begins to move means it begins. Okay, so we'll consider starting velocity to be 0. Okay, so then 0 to t of 2t dt, but this thing is multiplied by I cap plus 3 you can take outside, here also 2 you can move outside. Okay, so then 3 times t square dt multiplied by j cap. Just integrate this. So we know what is integration of this thing. So that is equal to, so on left hand side we'll just have, we'll have v, and on right hand side this 2 times of integration of t is t square by 2, lower limit is 0, so just take upper limit only, so it's t square by 2, the 2 will get cancelled, times I cap, plus you have 3 multiplied by, again here also lower limit is 0, it is t cube by 3 times j cap, right? So that is integration 3 2 gets cancelled, so you have t square into I cap, so v bar is equal to t square I cap plus t cube j cap, and what's the power? Power is equal to f bar dot v bar, so that is equal to, what's f bar? 2t into I cap plus 3t square times j cap, and you take its dot product with t square I cap plus t cube j cap. So what's that? That is equal to x component with x component, multiply x with x, 2 times t into t square, so that is 2 times t cube, plus y component with y component, so it is 3t square times t raised to 3 is 3t raised to 5, right? So 2t cube plus 3t raised to 5 watt. Okay, the power of the unit of power is watt. Okay, 3t cube plus 2t cube plus 3t raised to 5, so it is option B. Okay, did somebody find? Okay, Vishalini found it. Good. This is simple, right? And what is the unit of power? Unit is SI unit is watt. Okay, watt. And what is 1 watt? So power is work done per unit time. That means unit of work is joule. Okay, unit of time is second. So 1 watt is 1 joule per second. Right. So I'm sure you know that. Okay, everyone. Right. Let's see next one. A particle of mass m is driven by a machine that delivers a constant power k watts. If the particle starts from rest, the force on the particle at time t is. Tell me. Anyone? Particle of mass m is driven by a machine that delivers constant power k watts. If the particle starts from rest, so initial speed is 0, the force on the particle at time t is. Okay, let's find it out. So power, they say, is equal to k, and we know that it is force times velocity, because they are asking about the force. Okay, and then now power is constant, power is not changing, so you can say that work done okay. So I know k, I want to find out F, force, but I don't know what is V. So what I will do is I can use work energy theorem. Right, work done is equal to change in kinetic energy. I can say work done is equal to change in kinetic energy, final kinetic energy minus initial kinetic energy, right? So that is equal to, what is work done? So you know power is equal to work done divided by time. So work done is equal to power into time, so that is equal to k times t. Okay, it is power multiplied by time, right? Work done is equal to power times time. Okay, and this I have written using work energy theorem, WE theorem, let's say THM, right? Okay, so then work done is power into time. Okay, so I can say KT is equal to, right, W is equal to power into time, that is K times T, and therefore work done, which is equal to final kinetic energy minus initial kinetic energy, and for W I am writing KT, that's equal to final kinetic energy is half mv square. How much is initial? So body starts from, particle starts from rest, it is given, right? The particle starts from rest, so initial kinetic energy is 0. So KT is just equal to half of mv square. Okay, KT is just equal to half of mv square, and from there we can find out the velocity, right? Okay, T is there, no? Yeah, T is there in all of the options. We can find out velocity from here. So just move this velocity on this side, So because here we wanted to find out the force, force is equal to this k divided by velocity, right? And from here we can find out velocity from this equation. So v square is equal to 2kt, right? 2kt divided by m, that is v square, and therefore v is equal to square root of 2kt by m. But what do you want? You want force. So that force is equal to k by v. Okay, it's equal to k by v. So it is k divided by square root of 2kt divided by m. So that is the answer. Is it there? Okay. So move the m in numerator. So it will be root m, and k divided by root k is root k. So in numerator you will have root of mk divided by 2, root of mk by 2, and the t in the denominator can be root of mk by 2. It's there in option C. And in denominator you have root of t. So you can write it in the numerator as, or this thing is root of t is t raised to half. In numerator you can write it as t raised to minus half, right? So that is the answer. Root of mk by 2 multiplied by t raised to minus half, because you are moving it to numerator, right? So this is the answer. Okay, is this thing clear? Yes, no? Okay, everyone? Right, this is little bit lengthy, right? Okay, good. Then let's see next one. One coolie takes 1 meter to raise a suitcase through a height of 2 meters. Okay, but the second coolie takes 30 seconds to raise the same suitcase to same height. So this one is simple. The powers of two coolies are in the ratio of, tell me. First one takes 1 minute, second one takes 30 seconds. So who is faster? Second one is faster, right? Means second one is more powerful. Okay, in that scenario. And he takes 30 seconds, means he takes half of the time. So he is twice as much powerful, right? Yes, no? So what's the ratio? It's 1:2. Okay, option D, right? Everyone, what do we need to solve? Okay, we can just compare like this, right? So this is simple. Let's see next one. A car of mass m starts from rest and accelerates so that the instantaneous power delivered to the car has a constant magnitude p0. The instantaneous velocity of this car is proportional to, okay, tell me. It starts from rest again. So again you can make use of work energy theorem. Right? So work done is equal to what? Final kinetic energy minus initial kinetic energy. Work done is equal to change in kinetic energy, right? And you have power of constant magnitude p0. Work done is just equal to power into time. Okay, power is work done upon time. So work done is just equal to power into time, because power is constant. If power was not constant, then what do you need to do? Then in that case work done is equal to integral of p dt, right? If power is given by dw by dt, okay, in that case dw is equal to p dt. Okay, small work done in some small time dt is p dt, and work done would be equal to integration of p dt. But here the power is constant, that means work done is just equal to p0 times t. Okay, then you have final kinetic energy, that is half of m into v square. Initial kinetic energy is 0, right, because body starts from rest. Okay, and then you wanted the instantaneous velocity of this car is proportional to. So again you have move this 2 and m on other side, so you get that v square is equal to 2 times p naught t divided by m, right? 2 times p naught t divided by m, option B. Okay, let's see. So then p naught is a constant, m is a constant, so v square is proportional to t. That means v is proportional to, right, t raised to half. Okay, v square is proportional to t, so v is proportional to t raised to half, and that is option B. So this is simple, right, everyone? Okay, very simple. All right, so just remember, if you have constant power, okay, work done is equal to what? P naught times T or P times T. And if the power is not constant, then you need to integrate P dt to find out the work done. Okay. All right, let's see next one. A body projected vertically from Earth reaches height equal to Earth's radius before returning to the Earth. Okay, body is thrown from Earth, it goes till the height of Earth's radius before returning to Earth. The power exerted by gravitational force is greatest. Where is it greatest? At the highest position of the body, at the instant just before the body hits the Earth. It remains constant all through at the instant just after the body is projected. Tell me. Body is thrown from Earth, so you can think of rocket. Right, it's projected from Earth. It goes to some height. It goes to some height. Let's say till here. It goes and it returns back. It goes till there and returns back. Okay, where is the power maximum? This is the question. Power exerted by gravitational force. Anyone? Option D, at the instant just after the body is projected. Option D, option B, option B. At the instant just before body hits the Earth. Yeah, so this is correct. Option B is correct. Why? Because when the body leaves the Earth, okay, when the body is projected at that point, and when the body comes back, at both these cases the speed is same. Okay, the speed is same, but when the body comes back at that time, this velocity is in same direction as that of gravitational force. Gravitational force is downwards, right? So mg, let's say, okay, angle is 0. Very good. So initially you can say the speed was minus v, finally it's equal to v, right? And it is along g, right? It is along the gravitational force, or let's say gravitational force is just F, so it is acting downwards, right? So magnitude of velocity is equal, initial velocity and final velocity, magnitude wise it's equal, but direction is opposite, right? So power is maximum when, see, it is F bar dot V bar. So let's say this is V1, this is V2. Okay, so initial power, you can say, when it's projected, P1 is equal to F times V or F times V1 multiplied by cos of 180 degrees, right? It is dot product. Okay, cos 180 is minus 1. So what's the power? Minus of F times V1. And final power, let's say it's P2. So it is F times V2 multiplied by cos of 0, right? F bar dot V2 bar, you can say. So it is F times V2 into cos of 0. Cos 0 is 1. So it's F times V2. V1 is equal to V2, but the direction is opposite. So that's why power is more in the, or actually it's maximum in the second case. Okay, so this is clear. right? Good. Let's see next one. A particle of mass m starting from rest undergoes uniform acceleration. If the speed acquired in time t, capital T, is v, the power delivered to the particle is. A particle of mass m starting from rest undergoes uniform acceleration. If the speed acquired in time t is v, power delivered to the particle is. Tell me. Again, you can say power delivered is equal to what? So here we can find out average power delivered. It's equal to change in kinetic energy, final kinetic energy minus initial kinetic energy divided by time. Time is t here. Okay. So initial kinetic energy is 0. Particle starts from rest. Okay. So Ki is equal to, this is equal to 0. And what is final kinetic energy? It is half of mv square. So just put that, half of mv square divided by t. There can't be a question simpler than this. Half of mv square divided by t. Option D, right? Okay, this one was simplest. Yes, no? Okay. Option B, 5t square. Yeah, no problem. So half of mv square divided by t only. Okay, no problem. Let's see next one. Water falls from height of 60 meters at the rate of 15 kgs per second to operate a turbine. Okay, the losses due to frictional forces are 10% of energy. How much power is generated by the turbine? So this is simple. So loss is 10%, means output power is equal to 90% of input power, right? Loss is 10% means efficiency is 90%. Okay, so you can say efficiency is equal to 90% means output power by input power is equal to what? 90 by 100, that is 0.9, right? 90 by 100. Okay, so move P in on other side, so you get how much power is generated. So P out is just equal to 90 by 100 means 0.9 of P in. And what is P in? How much is the power delivered? So water falls from the height of 60 meters, okay, at the rate of 15 kgs per second, right? So the change in potential energy is equal to gain in kinetic energy, you can say. Okay, and water falls with some velocity means it is giving its kinetic energy to the turbine. Okay, it's giving its kinetic energy, which comes from what? The height from which it is dropped. Okay, it falls, right? So that is 0.9 multiplied by, so you want power, so it is mgh divided by t. Okay, what's given? Height is given, then mass that's falling per unit time is given, so m by t is given. Okay, so what's given? Mass falling per unit time. Okay, so that is 15 kgs per second. So just put the value, then there is nothing in the question. Right, so P out just equal to 0.9 multiplied by 15 multiplied by g is 10, height is 60. Okay, so that is 0.9 multiplied by 10 is 0.9 multiplied by 10 is 9. Then you have 15 times 6, how much? 90 times 9. Okay, nine times 90, okay, then times 10, so 8100, right? 8100, right? So that many watt, and it's given in kilowatts, so 8.1 kilowatts. Correct? So option C would be the answer. Okay, good. Let's see next one. How much water a pump of 2 kilowatt can raise in 1 minute to height 10 meters? Okay, so this is very simple. So power is just equal to mgh divided by T, but this is very old question. Okay, so recently there were questions like this, right? This one is very old. Okay, so mgh divided by T. So you want the height, so h is equal to just P times T by mg. Just put the values. So P is 2 kilowatt, means 2 into 10 raised to 3. Okay, and time is 1 minute, means 60 seconds, divided by mg. Oh, we want water, we want m, no? Height is given, we want m. Okay, so what do we have? We want m, so it is pt divided by g times h, right? Pt divided by g times h, then put the values. So it is 2 into 10 raised to 3. Option B, 2 into 10 raised to 3 times time is 1 minute, means 60 seconds, divided by g times h. So g is what? 10 multiplied by h is also 10. So this is 100. So 10 will remain from that. 60 times 2, 120 times 10, 1200. Right, 1200 kgs. Correct. Now how many liters is that? It is 1200 kgs. Yeah, 1 kg equals to 1 liter. So for water, okay, so for water 1 kg is equal to 1 liter. Okay, 1 kg is equal to 1 liter for water. So that's why it is 1200 liters. Right, so that's the answer. It's very, very simple. So these are two recent questions. So this is from NEET 2023 and the other one is from NEET 2022. This one, the potential energy of a long spring when stretched by 2 cm is U. If the spring is stretched by 8 cm, the potential energy in it will be. So this is option D. Yeah, we have solved this one and they have repeated it in NEET 2023, right? It was from some other year, right? Okay, let's see next one. The energy that will be ideally radiated by 100 kilowatt transmitter in 1 hour is. So this is very, very simple, right? So we know that power is energy spent or work done per unit time. What is energy spent? Let's say it is E. So E is just equal to P times T. E is just equal to P times T. So what is P? 100 kilowatt. So 100 kilowatt means 100 into 10 raised to 3, right? 1 kilowatt is equal to 1000 watts. So 100 into 10 raised to 3 and you have 1 hour, means it is 3600 seconds. Okay, just multiply this out. So this is 10 raised to 5, this is 10 raised to 7, 36 into 10 raised to 7 is the answer. Okay, that many joules, this is the answer. Now you can see that this is from NEET 2022, this one is from NEET 2023. So it's not like they don't ask simple questions, they do ask simple questions, right? So this one, they were very, very simple compared to the questions that we discussed, right? Yes, no?